Welcome to this gentle exploration of one of the universe's most mysterious and beautiful secrets. Tonight, we drift into the realm of cosmic strings, where reality itself may bear invisible scars from the very moment of creation. Picture, if you will, the fabric of space-time, not as the smooth, pristine canvas we often imagine, but as something far more complex and fascinating, a tapestry woven with invisible threads that stretch across the cosmos, defects so subtle they escape our direct perception, yet so profound they could reshape our understanding of everything that exists. In the quiet depths of modern physics, there exists a possibility, both humbling and extraordinary, that our universe carries within its very structure the memory of its birth, preserved not in light or matter, but in the geometry of space and time themselves. These theoretical wounds in reality are called cosmic strings, and they represent perhaps the most elegant intersection of the infinitesimally small and the incomprehensibly vast. There is something almost musical about the way cosmic strings emerge from our equations, not as crude imperfections, but as inevitable consequences of the universe's own mathematical poetry. They are the cosmic equivalent of the delicate fracture lines that appear when water freezes into ice, or the graceful boundaries where different crystal structures meet in cooling metal. Yet unlike these earthly analogies, cosmic strings would be defects in the very foundation of existence itself. Imagine walking through a vast cathedral at twilight, your footsteps echoing in spaces designed to inspire awe. Now imagine that this cathedral is the universe itself, and hidden within its architecture are columns and supports so thin they are essentially one-dimensional, yet so long they could stretch from one edge of the observable cosmos to the other. These invisible pillars would warp the space around them in ways that bend light and time, creating subtle distortions that speak to those patient enough to listen. The beauty of cosmic strings lies not just in their theoretical elegance, but in what they represent: a universe that bears the scars of its own magnificent becoming. Every great transformation leaves traces, and if cosmic strings exist, they would be the universe's way of remembering the moment when the fundamental forces that govern reality first learned to dance together. As we embark on this contemplative journey through the invisible architecture of space-time, we find ourselves standing at the threshold between the known and the unknowable, between the physics we can touch and measure and the deeper mysteries that require us to reimagine the very nature of existence. In the pages ahead, we will explore how these cosmic imperfections might have emerged from the primordial chaos of creation, how they would shape the universe around them, and why their discovery would fundamentally alter our place in the cosmic story. There is something profoundly calming about recognizing that even the universe itself might carry beautiful imperfections, reminders that perfection and beauty are not the same thing, and that sometimes the most profound truths are hidden in the spaces between what we can see. In the beginning, there was not chaos, but something far more interesting: a universe so young, so hot, and so full of potential that the very rules of reality had not yet settled into their familiar patterns. Tonight, we drift back to those first precious moments after the Big Bang, when our cosmos was less than a second old, and the foundations of everything we know were still fluid, malleable, waiting to crystallize into the stable universe we inhabit today. Picture, if you will, those earliest epochs when the temperature of everything that existed soared beyond 1 trillion degrees, so hot that the fundamental forces we know today were unified into a single primordial force. Imagine reality itself as a kind of cosmic soup where the ingredients that would eventually become electromagnetism, the weak nuclear force, and the strong nuclear force were all dissolved together in perfect, symmetric unity. There is something almost musical about the way physicists describe these phase transitions, moments when the expanding, cooling universe crossed critical thresholds and symmetries that had existed since the beginning suddenly broke apart like ice crystals forming on a winter window. As the cosmic temperature dropped below specific critical points, the unified force began to separate, much like how water vapor condenses into droplets, or how a piece of heated metal slowly cools and hardens into its final crystalline structure. But here is where the story becomes truly fascinating. Just as cooling water doesn't freeze uniformly everywhere at once, and just as crystals forming in solution create boundaries where different crystalline regions meet, the universe's phase transitions weren't perfectly smooth and uniform. In different regions of space, the symmetry broke in different ways, creating boundaries, cosmic domain walls, and along some of these boundaries, one-dimensional defects formed like cosmic scars. These defects, these cosmic strings, would have emerged naturally from the physics of symmetry breaking, as inevitable as the grain boundaries in cooling metal or the patterns that form when soap bubbles meet and merge. The universe, in learning how to become the structured cosmos we know, necessarily created these elegant imperfections, threads of the original unified field, trapped and preserved like fossils from the moment of creation. Consider the gentle beauty of this process. A universe so young, it still remembered being everything and nothing simultaneously, slowly teaching itself the rules that would govern the next 13.8 billion years. The cosmic strings would have formed not as mistakes or accidents, but as natural consequences of reality's own maturation. Growing pains, if you will, preserved in the fabric of space-time itself. As the universe continued to expand and cool, most of these primordial relics would have been diluted away, stretched beyond detection, or annihilated through interactions with their anti-defects. But some, the cosmic strings, could have remained, evolved, and persisted, creating a hidden network of one-dimensional structures threading through the cosmos, like the skeleton of creation itself. The remarkable thing about this cosmic adolescence is how it demonstrates that even the universe learned about itself gradually. Those phase transitions were moments of cosmic self-discovery, when reality figured out how to be stable, how to harbor complexity, how to eventually nurture stars and galaxies, and ultimately conscious beings capable of looking back and wondering about those first precious moments when everything was still possible and the architecture of existence was still being written in the cooling fires of creation. There is something profoundly beautiful about imperfection, about the realization that the most interesting and meaningful structures in our universe arise not from flawless symmetry, but from the elegant breaking of that symmetry. Tonight, we explore how cosmic strings would have emerged from this fundamental tension between order and complexity, between the perfect unity of the early universe and the rich diversity of the cosmos we inhabit today. In the quiet depths of theoretical physics, symmetry breaking is not destruction, but creation, the universe's way of choosing one path among infinite possibilities, like a pencil balanced on its point, finally tipping in a particular direction. Imagine the early universe as a vast landscape of pure potential, where every point in space faced the same cosmic choice: how to arrange the fundamental fields that would define the nature of reality in that region. The most elegant way to understand this is through what physicists call the Mexican hat potential, a beautiful mathematical surface that looks exactly like its name suggests. Picture a sombrero, where a marble placed at the very center of the crown sits in perfect, unstable equilibrium. This central point represents the symmetric state of the early universe, where all forces were unified and identical. But this perfect symmetry, like the marble at the peak, is fundamentally unstable. As the universe cooled, it was as if countless marbles rolled down from the crown of this cosmic sombrero, each one settling into the circular valley that surrounds the central peak, while every position in this valley is equivalent, representing the same broken symmetry. The marbles don't all end up in the same place. Different regions of space make different choices, creating boundaries where these cosmic domains meet. Now imagine what happens along these boundaries. In most cases, these domain walls would be unstable, dissolving away as the universe matured. But in certain special configurations, where three or more domains meet along a line, something remarkable occurs: the formation of a cosmic string. These one-dimensional defects become trapped features in space-time, unable to decay away, persisting like cosmic scars that preserve the memory of the universe's symmetry-breaking phase transition. The mathematics behind this process is breathtakingly elegant. Cosmic strings form when what physicists call a U1 symmetry breaks, essentially when the universe chooses a preferred direction in some abstract internal space, much like how a compass needle chooses to point north. But unlike a compass needle, which makes this choice uniformly across its entire surface, the universe made this choice independently in different regions, creating lines where these cosmic choices clash and cannot be reconciled. These strings would carry enormous energy, density, potentially as much as a mountain's worth of mass compressed into every meter of their length. Yet they would be so thin as to be essentially one-dimensional. They represent reality's attempt to preserve pieces of the original unified field, cosmic time capsules containing the physics of the universe's first moments, threading through the modern cosmos like invisible archaeological artifacts from creation itself. What makes cosmic strings truly remarkable is their inevitability. They are not exotic add-ons to cosmic evolution, but natural, almost necessary consequences of how a universe with our physical laws would develop. They emerge from the same theoretical framework that successfully describes the standard model of particle physics and the general theory of relativity, in breaking its perfect symmetry to become a universe capable of complexity and life. The cosmos would almost certainly have created these beautiful imperfections as a natural byproduct of its own maturation. Perhaps the most poetic aspect of cosmic string formation is how it demonstrates that the universe's richness, its capacity to harbor stars, planets, life, and consciousness, emerges directly from its willingness to abandon perfect symmetry. The cosmic strings, if they exist, would stand as monuments to this cosmic sacrifice, eternal reminders that perfection and meaningfulness are not the same thing, and that sometimes the most beautiful structures arise from the elegant breaking of perfect order. In the vast cathedral of the cosmos, where galaxies drift like islands of light across oceans of dark space, there may exist structures so subtle, so perfectly hidden, that they escape direct detection while fundamentally shaping the universe around them. These are the cosmic strings, theoretical objects that challenge our very conception of what it means for something to exist while remaining essentially invisible. Picture, if you will, a structure so paradoxical it seems almost mythical. A cosmic string would be infinitesimally thin, far thinner than a proton, approaching true one-dimensionality, yet potentially longer than the diameter of the observable universe itself. To grasp this extraordinary contrast in scale, imagine trying to visualize a piece of thread so fine it has essentially no width, yet so long it could wrap around the Earth billions upon billions of times. Now, multiply that length by factors that strain the very limits of mathematical expression, and you begin to approach the cosmic proportions we're contemplating. The energy contained within such a structure would be equally paradoxical and magnificent. Every meter of a cosmic string might contain as much mass energy as a terrestrial mountain. Mount Everest, perhaps, compressed into a line so thin it would be invisible even if it passed directly through your body. This represents energy densities so enormous they can only be compared to the conditions that existed in the first moments after the Big Bang, when the universe itself was compact enough to fit in a space smaller than a single atom. Yet for all their incredible energy density, cosmic strings would interact with ordinary matter in surprisingly gentle ways. Unlike black holes, which trap everything that ventures too close, cosmic strings would be almost ghostly in their influence on the world we inhabit. A cosmic string could pass through the Earth, through our solar system, even through our bodies, and we would likely never notice its presence directly. The matter we're made of, electrons, protons, neutrons, would simply ignore these cosmic threads, passing through them as if they weren't there at all. But space and time themselves would tell a different story. Here is where the true magnificence of cosmic strings reveals itself. They would warp the geometry of space-time around them in ways that are both subtle and profound. Einstein taught us that massive objects curve the space around them, and cosmic strings, with their extraordinary energy density, would create a unique type of curvature, not the inward pulling distortion of a black hole or star, but something far more elegant and strange. The space around a cosmic string would be fundamentally altered, yet in a way that preserves most of the properties we associate with normal, flat space-time. Imagine space-time as a vast sheet of paper and a cosmic string as an invisible line drawn across it. Now, imagine that sheet has been carefully cut along that line and a narrow wedge removed, then the edges sealed back together. The result would look almost normal from a distance, but close examination would reveal that a complete circle around the string would subtly fall short of 360 degrees. Space itself would have been given a permanent, invisible twist. This geometric distortion would create one of the most beautiful and subtle effects in all of physics. gravitational lensing without gravitational attraction. Light traveling through the universe would bend around cosmic strings not because it's being pulled toward them, but because the strings have literally altered the paths that light considers to be straight lines. Distant galaxies, seen through the influence of a cosmic string, might appear doubled, creating twin images separated by impossibly small angles. Cosmic mirages created by the invisible architecture of reality itself. Perhaps most remarkably, these cosmic threads would oscillate and vibrate like the strings of some universal instrument, generating gravitational waves that would carry the signatures of their motion across the cosmos. These ripples in space-time itself might one day be detected by our most sensitive instruments, providing the first direct evidence of these invisible monuments to the universe's primordial symphony of symmetry breaking. There is something deeply moving about the possibility that our universe might be threaded with these invisible structures, cosmic strings that preserve within their mathematical essence the memory of creation itself, yet remain so elusive that their discovery would require all the patience, ingenuity, and theoretical sophistication our species can muster. They remind us that the most profound truths about reality often hide not in plain sight, but in the spaces between what we can directly perceive, waiting to be revealed through the careful marriage of observation, mathematics, and wonder. In the quiet halls of Imperial College London in 1976, a brilliant physicist named Tom Kibble was contemplating one of the most profound questions in cosmology. How does a perfectly symmetric universe learn to become asymmetric without losing its essential beauty? His contemplation would lead to one of the most elegant theoretical discoveries in modern physics, the realization that the universe's transition from primordial unity to structured complexity would inevitably create cosmic strings threading through space-time like the hidden architecture of creation itself. Picture, if you will, the intellectual landscape of the mid-1970s when physicists were just beginning to understand how the fundamental forces of nature might have been unified in the universe's earliest moments. The standard model of particle physics was still taking shape, and cosmologists were wrestling with the profound implications of phase transitions in the early universe. Into this fertile ground of theoretical exploration came Kibble's insight, a recognition that would bridge the microscopic world of particle physics with the grandest scales of cosmic evolution. Kibble's genius lay not in complicated mathematics, but in a beautifully simple realization. When any system undergoes a phase transition, whether it's water freezing into ice, a magnetic material cooling below its critical temperature, or the universe itself transitioning between different states of physical law, defects inevitably form. These defects arise because different regions of the system cannot coordinate perfectly during the transition. They make different choices about how to break symmetry, creating boundaries where these choices meet and clash. The mechanism Kibble described has since become known as the Kibble mechanism, and it operates with almost musical inevitability. Imagine the early universe as a vast orchestra, where each region of space is like a musician trying to start a symphony without a conductor, without any way to coordinate across cosmic distances. Different sections begin playing in slightly different keys, at slightly different tempos. The boundaries between these cosmic musical phrases become the birth sites of topological defects, domain walls, cosmic strings, and other exotic structures. What makes cosmic strings particularly special in this cosmic symphony is their stability and longevity. Unlike many other defects that would quickly dissolve or annihilate, cosmic strings possess a topological protection, a mathematical property that prevents them from simply disappearing. They become permanent features of spacetime's geometry, like indelible ink marks on the fabric of reality itself. Kibble's work revealed that cosmic strings would form naturally during what physicists call grand unification phase transitions, moments when the electromagnetic and weak nuclear forces separated from their more fundamental unified state, or when even earlier, more exotic unifications broke apart. These strings would carry energy densities characteristic of these incredibly high energy transitions, preserving within their structure a fossil record of physics operating at scales we can barely imagine. The beauty of the Kibble mechanism extends beyond its elegant simplicity. It connects the abstract mathematics of field theory with the concrete evolution of our cosmos, showing how the universe's largest structures might bear the imprint of its most fundamental physical laws. Every cosmic string, if they exist, would be like a message written in the language of spacetime itself, carrying information about the universe's infancy across billions of years of cosmic history. Perhaps most remarkably, Kibble's theoretical framework suggests that cosmic strings wouldn't exist in isolation, but would form vast networks, cosmic webs of interconnected, one-dimensional defects stretching across the observable universe. These networks would evolve over time through complex interactions. Strings would oscillate, intersect, reconnect, and occasionally form closed loops that would radiate away their energy through gravitational waves. As we drift through this contemplation of Kibble's legacy, we find ourselves marveling at how a single theoretical insight, born from careful thought about symmetry and phase transitions, could reveal such profound possibilities about the hidden architecture of our cosmos. The cosmic strings that emerged from Kibble's equations weren't just mathematical curiosities. They were predictions about how the universe's most fundamental creative processes would leave their mark on the cosmic tapestry, threading through space and time as eternal reminders of creation's magnificent imperfections. There is something profoundly moving about recognizing that our universe's deepest truths often emerge not from human invention, but from patient listening to what the mathematics of nature itself whispers about the cosmos we inhabit. In the gentle mathematics of Einstein's general relativity, mass and energy do not simply occupy space. They teach space and time how to curve, how to bend, how to dance, in ways that guide the motion of everything within their influence. Tonight, we explore one of the most beautiful and subtle choreographies in all of physics, the way cosmic strings, if they exist, would partner with spacetime itself in an elegant dance that creates impossible geometries and transforms the very meaning of straight lines. Picture, if you will, spacetime not as the empty stage upon which cosmic events play out, but as an active participant in the cosmic story, a responsive medium that curves and flows according to Einstein's field equations, those 10 coupled differential equations that describe how matter tells spacetime how to curve, and how curved spacetime tells matter how to move. Into this exquisite mathematical relationship, cosmic strings would introduce a new kind of partner, linear concentrations of energy so dense they approach the limits of what spacetime can accommodate. The geometry around a cosmic string reveals one of the most remarkable features in all of theoretical physics, a spacetime that is almost, but not quite flat, unlike the dramatic curvature around a black hole, which creates an inescapable gravitational well, or the gentle dimpling around a star, which guides planetary orbits. A cosmic string would create something far more subtle and strange, a deficit of space itself. To understand this impossible geometry, imagine taking a perfectly flat sheet of paper and drawing a straight line across it. Now, imagine carefully cutting along that line and removing a thin wedge, not cutting completely through the paper, but removing a narrow slice so that when you bring the cut edges back together, they meet perfectly. But the paper now has slightly less total area. The line where you made the cut would be invisible, yet its presence would be revealed by a subtle but measurable effect. Any circle drawn around this line would have a circumference slightly smaller than its diameter would suggest. This is precisely the type of geometry that would surround a cosmic string, space that appears normal in almost every way, yet harbors a hidden deficiency, a subtle absence that can only be detected through the most careful measurements. The technical term for this is a conical singularity, but the poetry of it lies in recognizing that cosmic strings would create regions where space itself has learned new rules, where the familiar geometry of Euclid gives way to something more mysterious and beautiful. The gravitational effects of this exotic geometry would be unlike anything else in the cosmos. A cosmic string creates no inward pull, no gravitational attraction in the conventional sense. An object at rest near a cosmic string would remain at rest, feeling no force urging it toward the string. Yet light passing near the string would bend, not because it's being pulled by gravity, but because the string has literally redefined what light considers to be a straight path through spacetime. This creates one of the most elegant phenomena in theoretical astrophysics: gravitational lensing without gravitational attraction. Light from distant galaxies, traveling across the cosmos for billions of years, might encounter a cosmic string and find its path subtly deflected, not by being pulled off course, but by discovering that the course it thought was straight had been gently redefined by the string's influence on spacetime geometry. Perhaps most beautifully, cosmic strings would oscillate under their own tension, creating traveling waves that propagate along their infinite length at nearly the speed of light. These oscillations would generate ripples in spacetime itself, gravitational waves that would carry across the cosmos the signature of these primordial structures, like cosmic music played on instruments made of space and time themselves. The mathematical description of these effects emerges from Einstein's field equations when applied to the unique stress-energy configuration of a cosmic string, a linear distribution of energy that creates what physicists call a conical spacetime. The solutions are elegant in their simplicity, yet profound in their implications, suggesting that the universe might harbor structures that challenge our most basic assumptions about the nature of geometric space. As we contemplate this dance between cosmic strings and Einstein's spacetime, we find ourselves witnessing one of the most subtle and beautiful partnerships in all of the physics. Structures that reshape reality not through brute gravitational force, but through the gentle art of redefining the very stage upon which cosmic events unfold. In their interaction with space-time, cosmic strings would demonstrate that the most profound influences are often the most invisible, working not by overwhelming the systems around them, but by quietly teaching space and time themselves to move in new and magnificent ways. In the depths of theoretical physics, there exists a language so beautiful and precise that it can describe the birth of cosmic strings in equations that sing with mathematical poetry. Tonight, we drift into the realm of gauge theory and spontaneous symmetry breaking, where abstract mathematical symbols become the vocabulary for understanding how the universe learned to create structure from primordial unity, and how cosmic strings emerged as natural consequences of nature's most fundamental mathematical relationships. Picture, if you will, the mathematical landscape of gauge theory, a framework that describes how the fundamental forces of nature arise from underlying symmetries in the laws of physics. At its heart lies a profound insight. The most basic laws of nature remain unchanged when we perform certain transformations, like rotating our perspective or shifting our point of view. These symmetries, invisible to casual observation, form the mathematical foundation upon which all of particle physics rests. The story of cosmic strings begins with what physicists call a gauge field, a mathematical entity that permeates all of space, carrying the potential for force and interaction. Imagine this field as an invisible medium that fills the universe, much like the way a magnetic field fills the space around a magnet, but far more abstract and fundamental. In the early universe, this gauge field existed in a state of perfect symmetry, like a compass needle that could point in any direction with equal probability. But symmetries, like balanced pencils standing on their points, are often unstable. As the universe cooled and expanded, the gauge field was driven to choose a preferred direction, not in ordinary three-dimensional space, but in an abstract internal space that exists in the mathematics of the theory. This process, called spontaneous symmetry breaking, is like our cosmic compass needle finally settling on a preferred direction, breaking the perfect rotational symmetry it once possessed. The mathematical beauty of this process unfolds through what is known as the Higgs mechanism, the same fundamental process that gives mass to elementary particles. The gauge field, seeking its lowest energy configuration, rolls down from an unstable symmetric state into a stable asymmetric one. The mathematics describes this with elegant precision, a potential energy function that looks like the bottom of a wine bottle, with a flat center surrounded by a circular valley of lower energy states. When different regions of space make different choices about which direction to point in this internal space, boundaries form between these regions, mathematical domain walls, where different symmetry-breaking choices meet, and where these domain walls intersect in precisely the right configuration, cosmic strings crystallize out of the abstract mathematical relationships, becoming physical structures that embody the topology of the symmetry-breaking process. The gauge theory that describes cosmic strings is surprisingly similar to the theories that govern the electromagnetic force and the weak nuclear force in particle physics. The mathematical formalism involves what physicists call covariant derivatives, gauge transformations, and field strength tensors, terms that might sound intimidating, but which represent some of the most beautiful mathematical relationships in all of science. These equations describe how fields interact, how symmetries break, and how topological defects form with the inevitability of mathematical truth. What makes the mathematics particularly elegant is how it connects the microscopic scale of particle physics with the cosmic scale of cosmology. The same gauge symmetries that determine how electrons interact with photons also determine how cosmic strings would interact with the curvature of spacetime. The coupling constants that appear in particle accelerator experiments also appear in the equations that describe cosmic string formation in the early universe. The mathematical language becomes even more beautiful when we consider that cosmic strings are solutions to nonlinear field equations, mathematical structures that exist because they are self-consistent, because they represent configurations where all the forces and fields involved have found a perfect balance. They are, in a sense, mathematical poems written in the language of differential geometry and gauge theory, expressing truths about how symmetry and topology interact in the deepest levels of physical law. Perhaps most remarkably, the mathematics predicts that these structures would be topologically stable, protected by mathematical conservation laws that prevent them from simply dissolving away. Once formed, they would persist, not because they are physically robust, but because the mathematics of their existence prohibits their destruction. They become permanent features of spacetime's mathematical structure, as indelible as the theorems of geometry itself. As we contemplate this whispered mathematics of broken symmetry, we find ourselves in the presence of equations that blur the boundary between abstract mathematical truth and physical reality. The cosmic strings that emerge from these calculations are not arbitrary constructions of human imagination, but necessary consequences of the mathematical relationships that govern our universe, structures that must exist if the symmetries of nature break in the ways our most successful theories suggest they do. There is something deeply moving about recognizing that the universe's most exotic structures might emerge not from chaos or accident, but from the elegant mathematical necessity of symmetry breaking itself, written in equations so beautiful they seem to sing with the harmony of creation. In the grand symphony of theoretical physics, few concepts have captured the imagination quite like strings, those fundamental, vibrating entities that might form the deepest layer of reality. Yet tonight, as we drift through the mathematical landscape of modern physics, we encounter a beautiful irony. There are actually two completely different types of strings dancing through our equations, each offering its own profound vision of how the universe might be constructed. These are cosmic strings and superstrings, theoretical cousins that share a name but represent entirely different approaches to understanding the fundamental nature of existence. Picture, if you will, a cosmic string as we have come to know it, a one-dimensional defect in space-time itself, a scar from the universe's primordial phase, transitions stretching across cosmic distances with energy densities that boggle the mind. These strings are not fundamental constituents of matter, but rather emergent features of space-time geometry arising naturally from the symmetry-breaking processes that shaped our cosmos in its earliest moments. They would be large-scale structures, observable in principle through their gravitational effects, yet invisible to direct detection. Now imagine something entirely different. Superstrings, the hypothetical, fundamental constituents of all matter and energy in string theory. These theoretical entities exist at the Planck scale, dimensions so incomprehensibly tiny that they make atomic nuclei look like vast continents. Superstrings would vibrate in 10 or 11 dimensional spacetime, and their different vibrational modes would manifest as all the particles we observe: electrons, quarks, photons, and even the mysterious graviton that mediates gravitational force. The contrast between these two types of strings is both profound and poetic. Cosmic strings would be enormous, potentially infinite in length, yet infinitesimally thin, cosmic scale structures that preserve the memory of the universe's youth. Superstrings, on the other hand, would be utterly microscopic, far smaller than anything we could ever hope to observe directly. Yet they would be the fundamental building blocks from which all of reality is constructed. In the mathematical realm of string theory, these superstrings exist in a universe very different from our familiar three-dimensional space. String theory requires additional spatial dimensions, typically 6 or 7 extra dimensions beyond the 3 we experience daily. These extra dimensions are thought to be compactified, curled up so tightly at every point in space that they remain invisible to our senses and our instruments. It's a universe of extraordinary mathematical beauty, where the fundamental forces of nature emerge from the geometry of these hidden dimensions. Yet here is where the tale becomes truly intriguing. String theory itself can predict the existence of cosmic strings. In some versions of string theory, particularly those involving D-branes, multidimensional surfaces where strings can end, cosmic string-like objects, called cosmic superstrings, can form during cosmological phase transitions. These would be hybrids, combining elements of both theoretical frameworks. They would be macroscopic, cosmic scale objects like traditional cosmic strings, but they would also be fundamental string theoretic entities, vibrating with the quantum harmonics of superstring theory. The mathematical relationship between these two types of strings reveals one of the most beautiful aspects of theoretical physics: how different approaches to understanding reality can converge and complement each other. Cosmic strings emerge from relatively straightforward field theory and cosmology, while superstrings arise from attempts to unify quantum mechanics with general relativity at the most fundamental level. Yet both approaches suggest that string-like structures, whether emergent or fundamental, play crucial roles in the architecture of our universe. Perhaps most remarkably, both types of strings offer potential bridges between the quantum realm and the cosmic scale. Traditional cosmic strings could provide observational signatures of high-energy physics processes that occurred in the early universe, effectively turning our cosmos into a vast laboratory for studying physics at energy scales we could never achieve on Earth. Cosmic superstrings from string theory could do the same, but they would also carry information about the extra dimensions and fundamental structure of spacetime itself. The search for either type of string represents humanity's attempt to read the universe's deepest secrets, written in languages ranging from the topology of space-time defects to the harmonics of vibrating fundamental strings in higher dimensional space. Whether cosmic strings are scars from phase transitions or cosmic superstrings are echoes from string theory's hidden dimensions, their discovery would revolutionize our understanding of reality's fundamental nature. As we contemplate this tale of two theoretical frameworks, we find ourselves witnessing one of the most beautiful aspects of scientific inquiry: how different mathematical approaches to understanding reality can yield complementary insights, each illuminating different aspects of the cosmic mystery we seek to understand. In the end, both cosmic strings and superstrings remind us that the universe might be far stranger, far more mathematical, and far more beautiful than our everyday experience could ever suggest. A cosmos where the deepest truths are written in the language of strings, whether they stretch across galaxies or vibrate in dimensions we cannot see. In the vast concert hall of the universe, where silence has reigned for nearly 14 billion years, there may exist instruments of such extraordinary subtlety that their music can only be heard by the most sensitive listeners, detectors capable of feeling the rhythm of space-time itself as it dances to melodies played on cosmic strings. Tonight, we drift into the realm of gravitational wave astronomy, where the oscillations of these invisible cosmic threads would create ripples in the fabric of reality, carrying across the cosmos a symphony written in the language of curved space-time. Picture, if you will, a cosmic string as it moves through the universe, not the static, unchanging thread we might first imagine, but a dynamic, living structure under constant tension, like a guitar string stretched between cosmic distances. A cosmic string would vibrate with its own internal energy, creating traveling waves that propagate along its infinite length at nearly the speed of light. These oscillations would be driven by the string's own gravitational back reaction, a beautiful feedback loop where the string's curvature of space-time influences its own motion, creating a self-sustaining cosmic dance. The physics of these oscillations reveals one of the most elegant aspects of cosmic string dynamics. Unlike ordinary matter, which typically settles into stable, static configurations, cosmic strings are inherently dynamic. They cannot remain perfectly straight and motionless. The mathematics of general relativity demands that they move, that they curve, that they oscillate with patterns that depend on their history, their interactions, and the subtle gravitational forces that shape their evolution across cosmic time. As these cosmic strings vibrate and oscillate, they would generate disturbances that propagate outward through space-time itself, gravitational waves that carry the acoustic signature of these primordial structures across billions of light years. Unlike the gravitational waves from merging black holes or neutron stars, which create brief, violent crescendos in the cosmic silence, cosmic string, gravitational waves would produce more subtle, persistent melodies, continuous streams of space-time distortion that could last for millions or even billions of years. The mathematical description of this cosmic music is breathtakingly beautiful. The gravitational waves from oscillating cosmic strings would carry distinctive frequency signatures, unlike anything else in the known universe. They would produce what physicists call a stochastic gravitational wave background, a gentle, persistent whisper of space-time distortion that fills the universe like cosmic background radiation, but carried in the curvature of space and time rather than in electromagnetic waves. What makes this cosmic orchestra particularly fascinating is how it would evolve over time. Young cosmic strings, formed in the early universe, would have been highly energetic and chaotic, producing gravitational waves across a broad spectrum of frequencies. As the universe expanded and aged, these strings would have settled into more regular oscillation patterns, their gravitational wave output becoming more organized, more musical in its mathematical structure. The connection to modern gravitational wave detectors like LIGO, Virgo, and the future space-based detector, LISA, creates one of the most exciting prospects in contemporary astrophysics. These instruments, originally designed to detect the dramatic gravitational wave bursts from colliding compact objects, might also be sensitive enough to hear the subtle background symphony of cosmic strings, if such strings exist and if their parameters fall within the right range of frequencies and amplitudes. The search for cosmic string gravitational waves represents a unique form of cosmic archaeology, unlike electromagnetic astronomy, which shows us the universe as it appears in light. Gravitational wave astronomy would allow us to hear the universe's mechanical vibrations, to detect structures and events that produce no light at all. Cosmic strings, being essentially invisible to electromagnetic radiation, would reveal themselves primarily through their gravitational songs, melodies written in the mathematics of curved space-time. Perhaps most remarkably, different types of cosmic string networks would produce different gravitational wave signatures, like different instruments in a cosmic orchestra. Straight, infinite strings would create one type of signal, while cosmic string loops, closed curves that gradually radiate away their energy, would produce another. The reconnection events, where cosmic strings intersect and exchange segments, would create distinctive gravitational wave bursts like cosmic percussion, marking the rhythm of the string network's evolution. The prospect of detecting these gravitational waves carries profound implications for our understanding of fundamental physics. The frequency and amplitude characteristics of cosmic string gravitational waves would directly reveal information about the energy scale at which these strings formed, potentially providing our first direct observational window into physics at grand unification scales, energies trillions of times higher than anything we can create in terrestrial particle accelerators. As we listen to this possibility of a cosmic string orchestra playing its gravitational melodies across the universe, we find ourselves contemplating one of the most beautiful intersections of theoretical physics and observational astronomy. The same mathematical structures that emerge from our most abstract theories of particle physics and cosmology might be detectable as subtle modulations in the length of laser interferometer arms, as tiny stretches and compressions of space-time itself that reveal the universe's hidden musical architecture. There is something profoundly moving about the possibility that the universe might be singing to us in gravitational waves, and that among those songs might be the ancient melodies of cosmic strings, threads of primordial energy still oscillating with the rhythm of creation itself, their music carrying across cosmic distances and billions of years to reach our listening instruments on this small planet where conscious beings have learned to build detectors sensitive enough to hear the space-time symphony of the cosmos. In the gentle mathematics of general relativity, time is not the universal, flowing river we experience in our daily lives, but rather a coordinate woven intimately with space into the four-dimensional fabric of space-time. Tonight, we venture into one of the most mysterious and beautiful consequences of cosmic strings, their potential to create closed time-like curves, pathways through space-time that loop back upon themselves, creating the theoretical possibility of traveling into one's own past and raising profound questions about the nature of causality itself. Picture, if you will, the space-time around a cosmic string, that elegant deficit geometry where space has been given a subtle twist, where angles don't quite add up to what Euclidean intuition would expect. Now imagine what happens when cosmic strings move, when they oscillate through space at relativistic velocities, dragging their exotic geometry through the cosmic medium like cosmic scythes cutting through the fabric of reality itself. Under certain, very specific conditions, the relative motion of two cosmic strings can create something almost magical, regions of space-time where the normal forward flow of time becomes tangled, where the light cones that define the causal structure of reality tip and bend in such a way that a pathway exists from any event back to itself. These are the closed time-like curves, mathematical solutions to Einstein's field equations that permit, in principle, travel into one's own past. The physics behind this extraordinary possibility lies in the way moving cosmic strings drag space-time along with them, much like how a spoon stirred through honey creates swirling currents in the viscous medium. When two cosmic strings pass by each other at nearly the speed of light, their combined gravitational effects create a region where space-time itself becomes twisted into a complex geometry that permits these closed causal loops. Yet this is where the universe reveals its remarkable wisdom. The creation of closed time-like curves through cosmic string interactions requires incredibly specific conditions, precise alignments, exact velocities, perfect timing. The cosmic strings would need to be moving at nearly the speed of light relative to each other. Their paths would need to intersect at precisely the right angles, and the entire configuration would need to maintain its delicate balance for exactly the right duration. The mathematical beauty of these solutions emerges from the interplay between topology and causality in general relativity. The closed time-like curves are not violations of Einstein's theory. They are legitimate solutions to his field equations, as mathematically valid as the orbit of a planet around a star or the collapse of matter into a black hole. They represent regions where the geometry of space-time itself has become so exotic that cause and effect become entangled in ways that challenge our most basic intuitions about the nature of time. But the universe seems to possess an almost aesthetic sense about such matters. The creation of closed time-like curves through cosmic string interactions would be extraordinarily rare, requiring such precise cosmic choreography that it would likely occur only a handful of times, if at all, throughout the entire history and future of our observable universe. The cosmos appears to permit these causal paradoxes in principle, while making them practically impossible through the sheer improbability of the required conditions. Even more remarkably, quantum mechanics may provide its own elegant resolution to these temporal paradoxes when physicists attempt to analyze what would actually happen if someone could travel along a closed, time-like curve. They discover that quantum effects, the uncertainty principle, virtual particle creation, vacuum fluctuations, would likely intervene to prevent paradoxes from actually occurring. The universe at the quantum level appears to possess what some physicists poetically call a chronology protection mechanism, ensuring that causality remains intact even when general relativity permits apparent violations. The study of cosmic string time loops has led to profound insights about the relationship between causality, determinism, and free will in a universe governed by the laws of physics. These theoretical investigations reveal that the universe's permission of closed time-like curves in principle, combined with their practical impossibility, creates a kind of mathematical poetry. Reality explores the full space of logical possibility while maintaining the causal structure that makes meaningful existence possible. Perhaps the most beautiful aspect of cosmic string time loops is how they demonstrate the universe's remarkable self-consistency, even when general relativity permits the most exotic geometries imaginable. When space-time itself becomes twisted into configurations that would seem to violate causality, the deeper structure of physical law ensures that the logical consistency of reality remains intact. The contemplation of these temporal paradoxes carries us to the very edge of human understanding about the nature of time, causality, and existence itself. The cosmic strings that might create closed time-like curves would be threading through our universe, not just as one-dimensional defects in space, but as structures that probe the deepest questions about the relationship between mathematics and reality, between what is theoretically possible and what the universe actually permits. As we drift through this exploration of time loops and causal paradoxes, we find ourselves marveling at how cosmic strings, if they exist, would serve not just as fossils from the universe's youth, but as cosmic philosophers, raising through their very existence the most profound questions about the nature of time, causality, and the mathematical structure that underlies all of reality. There is something deeply comforting about recognizing that even when the universe permits the most exotic possibilities imaginable, it seems to possess an inherent wisdom that preserves the causal order upon which meaningful existence depends. In the great detective story of modern cosmology, the search for cosmic strings represents one of the most elegant and challenging investigations ever undertaken by human science. Tonight, we embark on a contemplative journey through the methods and strategies astronomers use to hunt for these invisible threads, exploring how the absence of direct evidence becomes its own form of cosmic poetry, and how the universe's most subtle structures might reveal themselves through the gentle art of gravitational forensics. Picture, if you will, the extraordinary challenge facing cosmic archaeologists. How does one search for structures that are essentially one-dimensional, that interact only weakly with ordinary matter, and that reveal themselves primarily through their influence on the geometry of space-time itself? It is like trying to detect the presence of invisible silk threads stretched across a vast, darkened cathedral by watching for the subtle ways they bend and deflect beams of light passing through the shadows. The primary method for cosmic string detection relies on gravitational lensing, the way these structures would bend light not through gravitational attraction, but through their alteration of space-time geometry. When light from distant galaxies travels across the universe for billions of years, encountering a cosmic string along its path would create one of the most beautiful and distinctive signatures in all of astronomy. The appearance of identical twin images of the same galaxy, separated by impossibly small angular distances. Unlike the lensing effects created by massive objects like galaxy clusters, which produce multiple distorted images arranged in complex patterns, a cosmic string would create what physicists call a double image with a very specific geometric signature. The two images would be nearly identical in brightness and spectral characteristics, displaced by an angle that depends on the string's energy density and distance from Earth. Most remarkably, there would be no time delay between light arriving from these twin images. Both would show the same variations in brightness simultaneously, revealing that they are truly different paths taken by the same photons. The mathematical precision required for this detection is breathtaking. Astronomers must measure angular separations that might be smaller than 1,000th of an arcsecond, equivalent to resolving details smaller than a human hair viewed from a distance of several kilometers. This requires not just the most advanced telescopes humanity has ever built, but also sophisticated image processing techniques and statistical analysis methods that can distinguish genuine cosmic string signatures from the countless other ways that galaxies might appear doubled or distorted in the cosmic deep field. Perhaps even more subtle and beautiful is the search for cosmic string signatures in the cosmic microwave background, that ancient light that has been traveling toward us since the universe first became transparent about 380,000 years after the Big Bang. Cosmic strings present at the time of the last scattering would have left their gravitational fingerprints on this primordial radiation, creating subtle temperature variations that follow very specific patterns dictated by the string's influence on space-time geometry. The Planck satellite and other cosmic microwave background missions have created the most detailed maps of the early universe ever achieved, revealing temperature fluctuations measured to a precision of a few millionths of a degree. Within these incredibly detailed maps, cosmologists search for the distinctive signatures that moving cosmic strings would have imprinted, linear patterns of temperature variation that would stand out against the more random fluctuations created by ordinary density variations in the primordial plasma. The search extends beyond electromagnetic signatures to the realm of gravitational wave astronomy. The LIGO and Virgo detectors, originally designed to observe the dramatic gravitational waves from merging black holes and neutron stars, have also begun searching for the more subtle, persistent gravitational wave background that oscillating cosmic strings might produce. This represents a completely different approach to cosmic string detection, listening for their mechanical vibrations in space-time itself, rather than looking for their optical effects on distant light. Future gravitational wave observatories, particularly space-based detectors like the planned LISA mission, would be sensitive to lower frequency gravitational waves that could carry the signatures of cosmic string networks evolving over cosmic timescales. These detectors would effectively transform our entire solar system into a gravitational wave antenna capable of detecting space-time distortions that change the distance between Earth and spacecraft by amounts smaller than the width of an atom. The statistical nature of cosmic string searches adds another layer of mathematical beauty to the investigation. Rather than looking for a single, definitive detection, astronomers must perform careful statistical analyses of large data sets, searching for patterns that would be extremely unlikely to occur by chance. They must distinguish between genuine cosmic string signatures and the countless other astrophysical phenomena that could mimic their effects. Cosmic scale process of elimination that requires both theoretical sophistication and observational patience. Perhaps most remarkably, the absence of detected cosmic string signatures has itself become scientifically valuable, providing increasingly stringent limits on the possible properties these structures could possess if they exist. Each null result narrows the parameter space where cosmic strings might hide, gradually constraining their possible energy densities, formation mechanisms, and evolutionary histories. As we contemplate this great cosmic survey, we find ourselves witnessing one of the most beautiful aspects of modern astronomy: how the search for invisible structures pushes the boundaries of observational technique, theoretical understanding, and data analysis methodology. The hunt for cosmic strings has driven innovations in gravitational wave detection, precision astrometry, statistical analysis, and cosmic microwave background analysis that benefit all of astronomy. There is something profoundly moving about recognizing that our search for these invisible threads represents humanity's attempt to read the universe's autobiography, written in the subtle geometric distortions that might preserve the memory of reality's most fundamental phase. Transitions across 13 billion years of cosmic history, in the vast theater of cosmic evolution, where galaxies form and dissolve across billions of years, like foam on an infinite ocean. There may exist structures so persistent, so fundamentally woven into the fabric of space-time itself, that they serve as the universe's eternal memory, networks of cosmic strings that evolve, interact, and reshape themselves across the entire history of the cosmos. Tonight, we drift into the contemplation of how these invisible threads would form vast webs stretching across space and time, creating a hidden architecture that evolves with the mathematical inevitability of a cosmic symphony written in the language of topology and differential geometry. Picture, if you will, the early universe shortly after the formation of the first cosmic strings, not a cosmos filled with isolated individual threads, but rather a vast interconnected network, a three-dimensional web of one-dimensional defects stretching across space in patterns of extraordinary complexity and mathematical beauty. These networks would have formed naturally as the universe underwent its primordial phase transitions, with strings intersecting, connecting, and creating a cosmic infrastructure as fundamental and pervasive as the space-time in which it exists. The evolution of these cosmic string networks reveals one of the most beautiful examples of emergent complexity in theoretical physics. Initially, the networks would have been dense and chaotic, with strings intersecting frequently and creating a tangled web of incredible intricacy. But as the universe expanded and cooled, these networks would have undergone a gradual evolution governed by their own internal dynamics and the expansion of space-time itself. a cosmic process of self-organization that continues across billions of years. The mathematics describing this evolution involves what physicists call the scaling solution, remarkable theoretical result showing that cosmic string networks naturally evolve toward a quasi-steady state where their statistical properties remain approximately constant even as the universe expands around them. This scaling behavior emerges from a delicate balance between the network's tendency to simplify itself through string interactions and the universe's expansion, which tends to stretch and dilute the network's overall density. At the heart of this cosmic evolution lies one of the most elegant phenomena in theoretical physics: cosmic string reconnection. When two cosmic strings intersect, they don't simply pass through each other. Instead, they reconnect, exchanging segments in a process that fundamentally alters the network's topology. Imagine two loops of string passing through each other and, at the moment of intersection, exchanging partners to form two new loops with different geometries. This reconnection process drives the network's evolution, causing it to constantly reshape itself in ways that are both mathematically predictable and aesthetically beautiful. These reconnection events would occur with a frequency that depends on the network's density and the string's velocities, creating a cosmic symphony of topological transformations. Each reconnection would release energy in the form of gravitational waves and potentially high-energy particles, making the evolving string network a source of ongoing cosmic activity across the universe's entire history. The network would essentially be alive, in the sense that it would be constantly changing, constantly interacting with itself, constantly evolving toward new configurations. One of the most fascinating aspects of cosmic string network evolution is the formation of closed loops. When strings reconnect in certain configurations, they can create isolated circular strings that separate from the main network. These cosmic string loops would then oscillate under their own tension, gradually radiating away their energy through gravitational wave emission until they eventually disappear, like cosmic soap bubbles that slowly evaporate into the vacuum of spacetime. The population of these loops would create a kind of cosmic ecology, with new loops constantly being born from network interactions, while older loops slowly decay through gravitational radiation. The size distribution and evolution of these loops would follow precise mathematical laws, creating patterns that could potentially be observed through their gravitational wave signatures or their effects on the cosmic microwave background. As we contemplate the evolution of cosmic string networks across cosmic time, we encounter one of the most remarkable predictions of the theory. These networks would serve as cosmic fossil records, preserving information about the universe's phase transition history across billions of years. The statistical properties of a mature cosmic string network would carry imprints of the conditions under which the strings originally formed, creating a kind of cosmic DNA that encodes information about physics at energy scales far beyond anything we can access through terrestrial experiments. The interaction between cosmic string networks and the large-scale structure of the universe adds another layer of complexity and beauty to their evolution. These networks would influence the formation of galaxies and galaxy clusters through their gravitational effects, while simultaneously being influenced by the matter distribution they help to shape. This creates a cosmic feedback loop where the invisible string networks and the visible matter distribution co-evolve across cosmic history. Perhaps most remarkably, computer simulations of cosmic string network evolution reveal that these systems naturally develop fractal-like properties, structures that exhibit similar patterns at different scales, creating a kind of cosmic self-similarity that spans orders of magnitude in length. The network would look statistically similar whether viewed at the scale of galaxy clusters or at much smaller scales, creating a hidden mathematical harmony in the universe's invisible infrastructure. As we drift through this contemplation of cosmic string networks and their evolution, we find ourselves witnessing one of the most beautiful examples of how the universe creates and maintains complex structure across vast scales of space and time. These invisible webs would represent the cosmos's capacity for self-organization, for creating persistent patterns that evolve according to their own internal logic while remaining intimately connected to the expansion and evolution of space-time itself. There is something profoundly moving about recognizing that the universe might harbor these invisible networks, cosmic tapestries woven from the mathematics of topology and field theory, evolving across billions of years according to rules written in the deepest laws of physics, creating a hidden architecture that connects the moment of creation to the present and extends into the infinite future, a cosmic web that remembers everything and forgets nothing, threading through space and time as the universe's eternal, invisible memory. In the quiet halls of observatories around the world, where astronomers spend their nights listening to the whispers of distant galaxies and analyzing the subtle patterns hidden in cosmic light, the search for cosmic strings has become one of the most patient and methodical investigations in modern science. Tonight, we reflect on where this great cosmic detective story stands today, examining what decades of careful observation have taught us about the possible existence of these invisible threads and what the current absence of definitive detection tells us about the hidden architecture of our universe. Picture, if you will, the current landscape of cosmic string research as a vast puzzle where every observational survey, every data analysis, every theoretical refinement adds another piece to our understanding, not always filling in the picture we expected to see, but gradually revealing the constraints within which reality must operate. The modern search for cosmic strings has become an exercise in cosmic cartography, mapping not just what exists in our universe, but also what doesn't exist, or at least what exists in quantities too small to detect with our current instruments. The most comprehensive searches have come from detailed analyses of the cosmic microwave background, that ancient light that carries within its temperature fluctuations the imprint of every significant structure that existed when the universe first became transparent. The Planck satellite, with its unprecedented precision in measuring these primordial patterns, has provided us with the most stringent limits yet on cosmic string networks. The data whispers to us that if cosmic strings exist, they must be far more subtle than many theoretical models predicted, their energy density constrained to levels that place them at the very edge of detectability. These observational limits carry profound implications for our understanding of the early universe's phase transitions. The absence of strong cosmic string signatures in the cosmic microwave background tells us something beautiful and important. Either cosmic strings don't exist at all, or they exist in a parameter regime that makes them extraordinarily elusive, threading through our cosmos with such delicate subtlety that they leave only the faintest traces in the universe's baby pictures. The gravitational wave observations from LIGO, Virgo, and other detectors have added another layer to this cosmic investigation. The background of gravitational waves permeating our universe shows no clear signs of the persistent stochastic signals that oscillating cosmic string networks would produce. This null result doesn't definitively rule out cosmic strings, but it does constrain their possible properties, suggesting that if they exist, their oscillations must be either too weak or too infrequent to create detectable gravitational wave backgrounds with current technology. Perhaps most intriguingly, modern cosmological simulations have revealed how cosmic strings would interact with the large-scale structure of the universe. The cosmic web of dark matter filaments along which galaxies form and evolve. These theoretical investigations show that cosmic strings could influence galaxy formation in subtle but potentially detectable ways, creating statistical correlations in galaxy positions and properties that might eventually serve as indirect evidence for their existence. The field of cosmic string phenomenology has evolved into a sophisticated branch of theoretical cosmology where researchers explore not just whether cosmic strings might exist, but what their existence would mean for our broader understanding of fundamental physics. Modern studies connect cosmic string properties to particle physics models, inflation theory, and the mechanisms that might have generated the matter-antimatter asymmetry we observe in our universe. One of the most beautiful aspects of current cosmic string research is how it demonstrates the patient, cumulative nature of scientific progress. Each negative result, each observational limit, each theoretical refinement contributes to a growing understanding of where cosmic strings might hide in the vast space of theoretical possibilities. The constraints we've established don't represent failures of the cosmic string hypothesis, but rather a gradual mapping of the boundary between the detectable and the undetectable, between the universe we can observe and the deeper realities that might lie just beyond our current reach. The modern perspective on cosmic strings also reveals how theoretical physics and observational cosmology have learned to dance together more gracefully than ever before. Theoretical models now incorporate detailed predictions about observational signatures, while observational surveys are designed with specific theoretical predictions in mind. This symbiotic relationship has produced increasingly sophisticated searches that probe multiple aspects of cosmic string physics simultaneously: their gravitational effects, their influence on cosmic microwave background patterns, their gravitational wave signatures, and their potential role in large-scale structure formation. Perhaps most remarkably, the current status of cosmic string research exemplifies one of the most profound aspects of scientific inquiry: how the search for a specific phenomenon often reveals truths that are more subtle and more beautiful than the original hypothesis. Even if cosmic strings are never definitively detected, the search for them has deepened our understanding of phase transitions in the early universe, gravitational wave astronomy, precision cosmology, and the relationship between particle physics and cosmic evolution. As we contemplate the current state of this cosmic investigation, we find ourselves witnessing science at its most patient and methodical. Researchers who spend decades refining techniques, analyzing data, and gradually constraining the possible properties of structures that may exist at the very limits of detectability. There is something profoundly moving about recognizing that our search for cosmic strings represents humanity's attempt to read the universe's most subtle autobiography, written in mathematical languages so delicate they require all of our technological and theoretical sophistication to even begin to decipher. The modern cosmological perspective on cosmic strings reminds us that the universe's deepest secrets often hide not in dramatic, obvious phenomena, but in the subtle patterns that emerge only through patient observation and careful analysis, truths that whisper rather than shout, and that reveal themselves only to those willing to listen with the quiet attention that profound mysteries deserve. In the gentle progression of cosmic time, where scientific discoveries unfold across generations like slow blooming flowers, reaching toward understanding, we stand at the threshold of a new era in the search for cosmic strings. Tonight, we drift into contemplation of the magnificent instruments that future generations will inherit, telescopes and detectors of such extraordinary sensitivity that they might finally reveal the invisible architecture threading through our universe, or alternatively, establish with unprecedented precision that such structures simply do not exist within the cosmos we inhabit. Picture, if you will, the next generation of space-based gravitational wave observatories, led by missions like LISA, the Laser Interferometer Space Antenna, that will transform our entire solar system into a gravitational wave detector of almost unimaginable sensitivity. Unlike the ground-based detectors that have already revolutionized our understanding of black hole mergers, these space-based instruments will be sensitive to much lower frequency gravitational waves, precisely the range where cosmic string oscillations might create their most distinctive signatures. LISA will consist of 3 spacecraft flying in formation millions of kilometers apart, using laser interferometry to measure changes in their relative positions with precision approaching the width of an atom. This extraordinary sensitivity will allow it to detect gravitational waves that would stretch and compress space by amounts so small they challenge the very limits of what measurement means. If cosmic strings exist and oscillate within the right parameter range, LISA might hear their gravitational songs as persistent background melodies, threading through the symphony of space-time distortions from across the observable universe. The beauty of future gravitational wave astronomy lies not just in its technological sophistication, but in its patience. The recognition that cosmic string signals might require years or even decades of accumulated observations to emerge from the background noise of other gravitational wave sources. Future detectors will need to operate continuously for extended periods, building up statistical evidence for subtle signals that individual events could never reveal. Ground-based gravitational wave detection is also evolving toward extraordinary new capabilities. The planned Einstein Telescope and Cosmic Explorer will represent quantum leaps in sensitivity, capable of detecting gravitational waves from cosmic string networks that would be completely invisible to current instruments. These future detectors will operate in underground facilities designed to isolate them from terrestrial vibrations using quantum-enhanced sensing techniques that push measurement precision toward fundamental physical limits. The search for cosmic string optical signatures will be transformed by the next generation of space telescopes, particularly those designed for high-precision astrometry, the measurement of stellar positions and motions. The European Space Agency's Gaia mission has already demonstrated how space-based astrometry can measure stellar positions with unprecedented accuracy, and future missions will extend these capabilities to even more distant objects and smaller angular separations. Imagine telescopes capable of detecting the tiny angular displacements that cosmic strings would create through gravitational lensing, measurements requiring precision equivalent to observing the width of a human hair from the distance of the moon. These instruments will systematically survey billions of stars and galaxies, looking for the telltale patterns that would reveal cosmic strings threading through the line of sight to distant objects. The James Webb Space Telescope and its planned successors represent another approach to cosmic string detection through their unprecedented ability to observe the early universe in infrared light. These instruments can peer deeper into cosmic history than ever before, potentially revealing signatures of cosmic string networks in the cosmic microwave background with resolution and sensitivity that ground-based observations cannot match. Perhaps most remarkably, future cosmic microwave background missions will approach the fundamental limit of what can be measured in the ancient radiation from the early universe. Planned space-based missions will map the polarization patterns in this primordial light with such precision that they might detect the subtle signatures left by cosmic strings present during the epoch of last scattering. These measurements will effectively photograph the universe at an age of 380,000 years, searching for linear features that would reveal cosmic strings stretching across the primordial cosmos. The integration of multiple detection methods represents one of the most exciting aspects of future cosmic string searches. Rather than relying on any single type of observation, future investigations will combine gravitational wave signals, optical lensing signatures, cosmic microwave background patterns, and large-scale structure correlations to create a comprehensive picture of whether cosmic strings thread through our universe. Artificial intelligence and machine learning techniques are already beginning to transform how astronomers search for subtle patterns in vast datasets, and future cosmic string searches will likely rely heavily on these computational approaches. Advanced algorithms will be trained to recognize the distinctive signatures that cosmic strings would create across multiple types of observations, potentially revealing patterns too subtle for human analysis to detect. The timescales involved in these future searches remind us of one of the most beautiful aspects of scientific patience. The cosmic strings we might detect would have formed in the universe's first moments, evolved across 13 billion years of cosmic history, and finally revealed themselves to instruments built by curious beings on a small planet orbiting an ordinary star. The detection, if it occurs, would represent the culmination of a cosmic story spanning from the universe's birth to the emergence of consciousness capable of reading its own creation narrative. As we contemplate this future landscape of cosmic string detection, we find ourselves witnessing one of the most remarkable aspects of human scientific endeavor: the willingness to invest decades of effort, billions of dollars, and the careers of countless researchers in the pursuit of phenomena that might not exist, but whose potential discovery would revolutionize our understanding of the cosmos. There is something profoundly moving about recognizing that these future telescopes and detectors represent humanity's patient commitment to listening to the universe's most subtle whispers, to reading its most delicate signatures, to pursuing truths so elusive they require the most sophisticated instruments our species can conceive, operated with the patient attention that cosmic mysteries deserve. The hunt for cracks in reality continues, carried forward by instruments of extraordinary beauty and precision, waiting patiently for the universe to reveal whether it indeed harbors these invisible threads from creation's dawn. In the quiet depths of philosophical contemplation about the nature of existence, there are few discoveries that would more fundamentally alter our understanding of reality than the definitive detection of cosmic strings. Tonight, we drift into reflection on how these invisible threads, if they exist, would transform not just our models of cosmology and particle physics, but our deepest conceptions about the architecture of space-time, the relationship between the visible and invisible universe, and our place within a cosmos far stranger and more mathematically profound than we currently imagine. Picture, if you will, what the confirmed existence of cosmic strings would tell us about the fundamental nature of space and time. These structures would represent direct evidence that space-time itself can harbor permanent defects, regions where the smooth geometric manifold that Einstein described develops irreparable tears and twists that persist across cosmic history. This would elevate space-time from a passive stage upon which cosmic events unfold to an active participant capable of maintaining complex, dynamic structure independent of the matter and energy it contains. The implications would ripple through our understanding of every scale of cosmic structure. If the universe truly harbors one-dimensional defects that stretch across cosmic distances, then the fabric of reality would be revealed as far more complex and layered than our current models suggest. We would inhabit a cosmos where invisible architectures thread through space, creating hidden connections between distant regions and potentially influencing the evolution of galaxies, dark matter distribution, and even the expansion of the universe itself. The discovery of cosmic strings would provide our first direct observational window into physics at the grand unification scale, energy densities that approach the Planck scale, where quantum mechanics and general relativity merge into a more fundamental theory we don't yet possess. Every cosmic string would be like a fossil accelerator, preserving within its structure information about physical processes that occurred at energies trillions of times higher than anything achievable in terrestrial laboratories. This connection between cosmic strings and fundamental physics carries profound implications for our understanding of the forces of nature. The existence of these structures would confirm that the electromagnetic, weak, and strong nuclear forces were indeed unified at high energies, and would provide crucial experimental data about how this unification breaks apart as the universe cools. We would essentially be using our entire observable universe as a laboratory for studying the most fundamental aspects of physical law. Perhaps most remarkably, cosmic strings would forge new connections between seemingly disparate areas of physics. Their existence would link cosmology with particle physics, general relativity with quantum field theory, and observable astronomy with theoretical mathematics in ways that would almost certainly reveal unexpected unifications and correspondences. The study of cosmic strings might provide crucial insights into string theory, quantum gravity, extra dimensions, and other theoretical frameworks that currently exist primarily in mathematical abstraction. The relationship between cosmic strings and dark matter presents another fascinating avenue for expanding our understanding of reality. Some theoretical models suggest that cosmic strings could serve as gravitational scaffolding along which dark matter accumulates, potentially explaining some of the large-scale structure we observe in the universe's matter distribution. If confirmed, this would reveal cosmic strings as active participants in cosmic evolution, helping to shape the very architecture within which galaxies and galaxy clusters form. The implications extend beyond physics into our philosophical understanding of existence itself. Living in a universe threaded with cosmic strings would mean inhabiting a cosmos where invisible structures of almost unimaginable scale connect distant regions of space in ways that transcend our ordinary experience of locality and separation. These connections would be topological rather than causal structures that exist in the mathematical relationships between different regions of space-time rather than in the flow of information or energy between them. The temporal implications are equally profound. Cosmic strings would represent structures that formed in the universe's first moments, yet persist essentially unchanged across cosmic history. They would be temporal bridges connecting the physics of creation with the contemporary cosmos, carrying information about the universe's birth across billions of years of expansion and evolution. In a very real sense, cosmic strings would make the entire universe a repository of its own history. The discovery of cosmic strings might also revolutionize our approach to the deepest unsolved problems in cosmology: the nature of dark energy, the mystery of cosmic acceleration, the problem of cosmic fine-tuning. All of these might find new approaches through the study of how cosmic string networks evolve and interact with the expanding space-time background. These structures might provide crucial, missing pieces in our cosmic puzzle. Perhaps most beautifully, the existence of cosmic strings would confirm that our universe possesses what we might call mathematical memory, the capacity to preserve within its geometric structure the abstract mathematical relationships that governed its earliest evolutionary phases. This would elevate mathematics from a tool we use to describe reality to a constituent element of reality itself, woven into the very fabric of space-time, in forms that persist across cosmic ages. The implications for our search for fundamental truth would be equally transformative. Cosmic strings would demonstrate that some of the most profound aspects of reality exist not in dramatic, obvious phenomena, but in subtle geometric relationships that require our most sophisticated theoretical and observational techniques to detect. They would confirm that the universe's deepest secrets often hide in the spaces between what we can directly perceive As we contemplate these far-reaching implications, we find ourselves standing at the edge of a potential revolution in human understanding, one that would reveal our universe as far more interconnected, more mathematically sophisticated, and more mysteriously beautiful than our current theories suggest. The cosmic strings threading through space would not just be astrophysical objects, but ambassadors from the deepest levels of reality, carrying messages written in the language of topology and differential geometry from the moment of creation to conscious beings, capable of reading their mathematical poetry. There is something both humbling and exhilarating about recognizing that our search for these invisible structures represents humanity's attempt to understand not just what exists in our universe, but what existence itself means in a cosmos where reality and mathematics merge into a unified, elegant architecture that connects the smallest scales of quantum mechanics with the largest scales of cosmic evolution. In the gentle quiet of cosmic contemplation, as we reach the end of our journey through the theoretical landscape of cosmic strings, we find ourselves dwelling in a universe that may be far more mysterious, more mathematically elegant, and more profoundly interconnected than our everyday experience could ever suggest. Tonight, as we bring our exploration to a close, we reflect on what it means to live within a cosmos that might harbor invisible architecture, threads of primordial energy that connect the moment of creation to the present moment, weaving through space and time a hidden tapestry of such subtle beauty that its very existence challenges our most fundamental assumptions about the nature of reality. Picture, if you will, stepping outside on a clear night and gazing up at the star-filled sky, knowing that threading through that vast darkness might be structures so thin they approach true one-dimensionality, yet so long they could stretch from one edge of the observable universe to the other. These cosmic strings, if they exist, would be passing through the space around you, through your body, through the earth itself, yet remaining completely invisible and intangible, present everywhere, influencing nothing directly, yet potentially shaping the cosmic architecture that makes your existence possible. There is something profoundly moving about this possibility that we might live within a universe that carries within its very geometric structure the memory of its own birth, preserved not in light or matter that we can touch and measure, but in the curvature of space-time itself. Every cosmic string would be like a cosmic fossil, a mathematical poem written in the language of topology and field theory, carrying information about the universe's infancy across 13 billion years of expansion and evolution. The invisible architecture of cosmic strings speaks to one of the most beautiful aspects of scientific discovery: how the universe's most profound truths often hide not in dramatic, obvious phenomena, but in the subtle relationships that exist just beyond the edge of our perception. If cosmic strings thread through our cosmos, they would remind us that reality extends far beyond what our senses can directly apprehend, that the visible universe represents only a small fraction of the mathematical structures that might define the true nature of existence. Living in a universe with cosmic strings would mean inhabiting a cosmos where abstract mathematical relationships possess physical reality, where the solutions to differential equations become actual structures threading through space and time. This would elevate mathematics from a tool we use to describe reality to a fundamental constituent of reality itself, suggesting that at the deepest level, The universe might be mathematical, not just in its behavior, but in its essence. The patience required to search for these invisible structures reflects something beautiful about the human scientific endeavor. Astronomers and physicists dedicate their entire careers to the pursuit of phenomena that might not exist, building instruments of extraordinary sensitivity to listen for whispers that might never come, analyzing data with meticulous care in search of patterns so subtle they could easily be overlooked. This represents a form of cosmic devotion, a willingness to spend lifetimes in service of understanding, regardless of whether that understanding arrives within any individual human lifespan. The cosmic strings threading through our theoretical models serve as metaphors for all the invisible architectures that might structure our reality. Dark matter that outweighs ordinary matter by 5 to 1. Dark energy that drives the accelerating expansion of space itself. Quantum fields that permeate every cubic centimeter of apparently empty vacuum. Extra dimensions that might exist in parallel to the 3 spatial dimensions we experience. We find ourselves suspended within a cosmos where the visible represents only the surface of far deeper, more complex, and more beautiful underlying structures. Perhaps most remarkably, our search for cosmic strings demonstrates how consciousness has emerged within the universe to contemplate its own foundations. We are arrangements of atoms and molecules that the cosmos has assembled to study itself, to build instruments capable of detecting its most subtle features, to develop mathematical languages sophisticated enough to describe phenomena that exist at the very limits of the detectable. In seeking cosmic strings, we participate in the universe's ongoing project of self-discovery. The beauty of cosmic strings lies not just in their potential existence, but in what they represent about the relationship between theoretical physics and reality. These structures emerged from the mathematics of gauge theory and cosmology before anyone knew how to search for them observationally. They demonstrate how mathematical truth can lead to physical prediction, how abstract theoretical relationships can reveal concrete possibilities about the structure of space-time itself. Whether or not cosmic strings are ever definitively detected, they have already enriched our understanding of what kinds of structures are possible within a universe governed by the laws of physics we have discovered. They have driven innovations in gravitational wave astronomy, precision cosmology, and theoretical physics that benefit our understanding of reality, regardless of whether these specific structures actually exist. As we drift toward the end of this contemplation, we find ourselves inhabiting a moment of extraordinary privilege, living at a time when our species has developed the theoretical sophistication to imagine cosmic strings and the technological capability to search for them. We exist during a brief window in cosmic history when conscious beings can contemplate the invisible architecture of reality and attempt to read the mathematical poetry that might be written in the geometry of space-time itself. The cosmic strings that may thread through our universe serve as reminders of the profound mystery that surrounds us. They suggest that reality extends far beyond the familiar world of our daily experience, reaching into realms of such mathematical subtlety and geometric elegance that their contemplation approaches the mystical. Yet this mystical quality emerges not from supernatural belief, but from the rigorous application of scientific method to questions at the very edge of human understanding. In the end, the poetry of invisible architecture lies in recognizing that we live within a cosmos of almost infinite depth and complexity, where the search for truth requires not just empirical observation, but mathematical imagination, theoretical courage, and the patient willingness to listen for whispers that might be carrying messages from the very foundations of existence. Whether cosmic strings thread through our universe or remain forever in the realm of theoretical possibility, they remind us that reality is far stranger, far more beautiful, and far more worthy of our wonder than we could ever have imagined. There is something deeply comforting about recognizing that our universe might harbor such profound mysteries, invisible structures that connect the deepest levels of mathematical truth with the concrete reality we inhabit, threading through space and time as eternal reminders that existence itself is more magnificent than we can fully comprehend.